Hello everyone, this is part 2 of section 16.3, path independence and conservative vector fields. Last time we saw an example where we found the potential function. We first verified it was conservative or path independent. Then we found the potential function and evaluated the integral based on that potential function. So now we're going to see a 15-point problem, or might even be worth 20 points. It's a 200-point final, but this will definitely be on the final exam. Something very similar to this. You'll have one to practice in the review as well. And we're given a vector field. So here's f of x. And remember the way the vector field is defined. The function in front of the I is considered to be m, and the function in front of the j is considered to be n. And if it's conservative, then the partial of m with respect to y must equal the partial of n with respect to x. So if conservative, okay, this was based on our previous definition to recall. So recall from last time we had that definition that partial of m with respect to y has to equal partial of n with respect to x. Okay, so partial of m with respect to y is, since m is, if you want to write this, m is 3x squared plus y, then x squared, 3x squared is a constant, so its derivative is 0, derivative of y is 1. Okay, n is x plus 2y, and the partial of n with respect to x is derivative of x is 1, y is a constant, so the derivative of 2y is 0. So therefore, we have that the partial of m with respect to y is equal to the partial of n with respect to x. So then we've proven that they're conservative, or that the vector field is conservative. Okay, now we want to find that potential function. Now remember that with the potential function, we have the statement that f of xy, the vector field f of xy, is negative del of p, the potential function, which is negative del of p is really the partial of p with respect to xi, as we had shown in the last lesson, plus partial of p with respect to yj. Okay, so flashing back to that, here's what we showed del of p was, right? So then we have that statement. So what I did in the last example was I considered calling Roman numeral 1 the fact that del of p, or the partial of p with respect to x, has to be equal to m, because f of xy, again, is mi plus nj. So this has to be m and then I plus n and j. And we'll worry about the negatives later. That we'll find out p, and then we'll take the negative of it to make everything work, and we'll even verify that. But in any event, we could say that del of p with respect to x then is, okay, m is 3x squared plus y. Okay, so then if we want to find the potential function, p, we're going to integrate with respect to x. And so I always introduce functional notation here. You don't have to. But p of xy then is the integral of this with respect to x. So integrating 3x squared, we get 3x cubed over 3, or x cubed. Y is a constant, integrating y. So it's like integrating 1 with respect to x, we get x, so plus xy. And then we have to include a constant of integration. And since we integrated with respect to x, where y was a constant, that constant could be a function of y. So as we noted in the last example, we'll call that constant g of y, because since y was a constant, that constant could be a function of y. Okay, so then the second thing is to impose the condition that the partial of p with respect to y must be equal to n, wherever you want to look for that. So therefore, at this point, we'll take the partial of p with respect to y. Okay, the derivative of x cubed would be 0 because x is a constant. Derivative of xy, x is a constant. Derivative of y is 1, so we just get x. And then plus, in general, the derivative of g of y would be g prime of y. And our goal here is to find g of y. So now we can impose the second condition. The fact that the partial of the potential with respect to y has to be equal to n. So therefore the partial of p with respect to y is now equal to, okay, look at either place, n was x plus 2y. But actually, I'm sorry, what we'll do is we'll replace partial of p with respect to y, of course, by what we just found. So x plus g prime of y must equal, okay, and then n is x plus 2y. Okay, and what happens here is what happened in the previous example, which always does. Any term containing an x will vanish, and you'll just get a function, g prime of y, should always come out to just be a function of y, in this case 2y. And then we can integrate that to get g of y. So then g of y would be 2y squared over 2, or just y squared. We'll add a constant of integration at that point, call it c. And so then we have that p of xy can be equal to x cubed. So now we're going back up here. And we're just replacing g of y by what we just found. Okay, so then we account for the opposite. So we take p of xy to be equal to minus the function x cubed plus xy plus y squared, and then we'll just shove the c off to the right. Okay, so just as a little check, so that's our potential function. Okay, just as a little check, remember that the f of xy has to be equal to del of p, negative del of p. So consider negative del of p is minus the partial p with respect to x times I plus the partial p with respect to y times j. and that's equal to minus, okay, here's p of xy, so the partial p with respect to x would be, okay, let me put brackets here, because that's a negative, and then we've got 3x squared, derivative of xy with respect to x would just be y, and derivative of y squared, y is a constant, so that's 0, so that times I, okay, and then plus, we have minus, and then in parentheses the partial p with respect to y. Now x is a constant, so derivative of x cubed, 0, derivative of xy is just x, and derivative of y squared, 2y, and that's times j. So then this shows that negative del of p is, just distribute the negative, let's leave it as 3x squared plus y times I, and distributing the negative, this becomes positive, so plus, and let's leave it as x plus 2y times j, and notice that that is the actual function, f of x, y. There's up here, f of x, y, there's your 3x squared plus yi, x plus 2yj, and so this is f of xy. So we basically verified that it is in fact true, the function we found. Okay, so now they want us to use p of xy, the potential function that we just found, to evaluate the integral, where c is the line segment from 0, 0 to 416. So the integral of f dot dr is equal to, okay, from this is from our earlier theorem. It's the potential at the starting point minus the potential at the ending point. And so this is going to be, in our case, p of 0, 0. If you wanted to say, yeah, we'll just do that. Say p of 0, 0 minus p of 416. Okay, and really what we're doing here, and this will come into play in the next part of this example, we're starting at 0, 0, and we're going to, and that's a scale, of course, .416. So we're going along that path. And so that's just going to be equal to, we use the potential function we found, okay, which is right here. And so it's going to be minus, just say a big 0, and then minus a minus 4 is x, 16 is y, 4 cubed plus 4 times 16 plus 16 squared. Okay, that's 0, double negative makes positive. 4 cubed, 64. 4 times 16. 64. And then 16 squared plus 256. Okay, and then that gives us 384. Okay, so that's showing it by using our special theorem regarding the potential function. But now, here's the cool part. Part D, what we want to do is show by direct calculation where C is the curve from 0, 0 to, again, not to scale, 416. So that would be the line, okay, y equals mx plus b, the intercept 0, and the slope here is 4, change in y over the change in x. So that's the line, y equals 4x, which is basically a given, right? So from 0, 0 to 416. Okay, so now they want us to show this by direct calculation. So first off, we know that the function f is equal to, okay, that was the given, 3x squared plus y times I, and then plus x plus 2y times j. And we have to evaluate f dotted with r. Now remember that r is equal to or r is equal to xi plus yj, where x and y are functions of t. But we could say that dr then is dxi plus dyj, and then we can calculate f dot r. Or f dot dr, excuse me. So this would just be, if you want to show it, I guess, real formally, 3x squared plus y I plus x plus 2y j dotted with dr, which was dxi plus dyj we get that f dot dr. Okay, so recall dot products, I dot I is 1, j dot j is 1, I dot j 0, j dot I 0, so we just get 3x squared plus y dx, and then plus x plus 2y times dy. So now we have to evaluate the integral of f dot dr along this curve is the integral from 0, 0 to 416 of what we just found, 3x squared plus y dx plus 2y dy. And at that point, we have to get everything in terms of anything that belongs with dx, we need to get in terms of x, And anything that belongs with dy, we need to get in terms of y. So we have that y equals 4x, so we can make that substitution. And solving for x, we'd have that x equals y over 4, or 1/4 y, whatever you want to say. So therefore, this y, I want this all to be in terms of x. So this y we're going to replace by 4x. And this one we want all to be in terms of y. So this x we're going to replace by 1/4 y. Okay, so then this becomes the integral. Okay, with regards to the x coordinates, this will be the integral from 0 to 4 of 3x squared plus 4x with respect to x. And then we'll have plus the integral with regards to the y coordinates. We're going from 0 to 16. And then replace this x by 1/4 y plus 2y, and that's all with respect to y. Okay, and now we can do the integration. And so this becomes 3x cubed over 3, so just x cubed, 4x squared over 2, so plus 2x, evaluated from 0 to 4, and then plus, this becomes 1/4 y squared over 2, so 1/8 y squared, 2y squared. I suppose I could have combined those, but 2y squared over 2 plus y squared, evaluated from 0 to 16. Okay, so that gives us 4 cubed plus 2 times 4 minus a big 0 plus, a big plus here, 1/8 times 16 squared plus 16 squared minus a big 0. Okay, and crunching that down here, we get 64 plus 8, or, I'm sorry, 64 plus, oh, I made a mistake here. I think I said it. I think I said this was 2x squared. In any event, make sure you make that correction. So 64 plus 32 is 96. And then plus, if you crunch this excuse me, if you crunch this down, 16 squared over 8 plus 16 squared, you might want to use a calculator, get 288, and that gives us 384. And so that checks with, that's what's really cool about this, it checks with what the potential function that we just used in that part C. Alright, now, if you think that's exciting, watch this. Now we're going to evaluate the same integral, but taking a different path. Because remember, we said this is path independent, right? And so what we're going to do is we're going to take a path, instead of directly from start to finish, like we did in that last, in part D. Okay, we're going to take a path from 0, 0 to 4, 0. That's going to be C1. And we'll call this C2. 4, 0 to 416. Okay, so we're getting to the same endpoints, but we want to show this in a different way. So the first thing is to recall that f dot dr, we won't do it over again, but that was 3x squared plus y dx, and then plus x plus 2y dy. Okay, so that was from our work up here, right? So we're not going to do that over again. And now consider the path along C1. Okay, so this is where you have to examine the graph and notice something about that path, in particular that x is changing, but y is not changing, and at the same time y is always 0. So two things that we could note are that y is 0 and the differential dy is 0. Because there's no change in y, so that's why dy is 0. And y is always 0 because we're always along the x-axis. So, therefore, the integral along C1 of f dot dr becomes the integral from, the only thing that's changing is x is going from 0 to 4, and if y is 0, this becomes just 3x squared times the differential dx. And notice that the dy is 0, so this term drops out. So that's all we have for that. Integrating, we get 3x cubed over 3, or x cubed, evaluated from 0 to 4, and that's 4 cubed minus 0 cubed, so 64. So that's the work done along C1. And then along C2, okay, so you have to take a look at the graph and determine what's constant and what's changing and what's not changing. And so along C2, x is always the same. X is always fourths because you've got the vertical line. So y is changing, right, as you go along C2. So we could state that x is 4. Then here's the important part, the differential. See, y is changing, so dy is changing, but x is not changing. So therefore we could say that dx is 0. So then the curve, the work done along curve C2 is going to be equal to, okay, the integral from, and y now is changing from 0 to 16. And then in the function, if dx is 0, this term drops out, and x is always 4, so this x can be replaced by a 4. So we'd have 4 plus 2y with respect to y. And then we can integrate that. That gives 4y plus 2y squared over 2 is just y squared, evaluated from 0 to 16. And so that's 4 times 16 plus 16 squared minus a big 0. And if you crunch all that out, you get 64 plus 256 is 320. And then we verified, because 64 plus 320 is 384. And so pretty neat to actually see that path independence concept and prove it. So that's going to be like I don't know, 15 or 20 points. I'll tell you once we start talking about the actual review for the exam and such. But that 5-part question, definitely something you will expect to see on the final exam. All right, so that's the end of 16.3. We'll come back when you're ready.